very much for setting up this very nice workshop and for giving me or forcing me to speak. I've had the idea that I would tell you, so Miguel told you about no global symmetries, and I had the idea that I would tell you about two of the core ideas of the Swampland program that are closely related to no global symmetries and go beyond it, which is the weak gravity conjecture and the distance conjecture. I think in the end, mostly I'll tell you about the weak gravity conjecture, but with a little bit about the distance conjecture. It's a little bit much to fit them both into one talk. But I'll say something about both of them. Okay. So, all this. Core ideas in the Swampland program. Really, the Swampland program, you might say, starts with these conjectures because no global symmetries goes back farther. It's older than even the word Swampland. Of course, it's really where a lot of things come from. But as Miguel told you, it has limitations. Okay, so let me first say a little bit about what makes a good Swampland conjecture. So if we were trying to figure out, what are the general properties of quantum gravity, and we don't have any first principles idea of what quantum gravity is, so we can't prove anything a priori, how can we guess? We have some amount of data, of course, to compare to. We have string theories we can compare to. But there are some principles that are useful for formulating Swampland conjectures. One thing is that we want to, the whole idea of Swampland is to make some general guesses, not to say, oh, I really like heterotic string theory. Heterotic string theory seems to do this, so I think that must be true. We have to look at the whole landscape. And we want to make guesses that are framed in general terms. Maybe in EFT language, for example. Something that's not specific to one construction. Ideally, and that's well motivated. But of course, we don't really know what quantum gravity is, so I should really say heuristically. And then we can fight about, whether it's a good reason or a bad reason. But at least Miguel's already told you about no global symmetries, which is maybe a bit beyond heuristically well motivated. So if you can link things to no global symmetries, then maybe you're doing well. Very good to formulate sharp conjectures. Maybe one way of saying what a sharp conjecture is a conjecture that's as close as possible to being wrong. And the reason why that's good is because ideally we'd like to be able to possibly falsify the wrong conjectures and identify the ones that are left over. Right? If we just formulate conjectures that are so far out of reach that we can't test them, then we're never really going to know, based on what we know about string theory, are those conjectures true or not? They're just guesses. Of course, we don't want to look at the string landscape and think about really fine details and say, well, this must always be true because we have only so much data. Right? Think about simple ideas. Maybe once you start to have some Swampland conjectures, it's good to be connected to other Swampland conjectures or principles. I already mentioned, again, being connected to no global symmetries is a good place to start. And of course, the final thing that's nice and good place to check your Swampland conjectures by looking at lots and lots of string constructions. And again, that's why it's important to think about sharp conjectures, right? If you just make some vague statement, then you just look at a given string construction, and you're like, well, if I kind of tweak this, it looks like it's okay, and then you're not really doing very much. If you make a very sharp conjecture, then anytime you pick up a string construction, there's a danger that you're going to find a counterexample. Then if you never do, it becomes much more convincing that you're onto something. So on the other hand, we might go about Swampland because we want to learn about phenomenology or the real world. And then we have a different set of principles that we'd like to satisfy. So we might want to have a conjecture that contains non-SUSY theories. It's hard to construct non-SUSY theories in string theory with full control, so maybe if we had a good Swampland conjecture, that would give us guidance. I want a conjecture that addresses cosmology, so getting away from the lamppost of Minkowski and ADS to other situations. Might not want to rely on parametrically weak coupling. You might want to formulate conjectures that have actual experimentally testable consequences. After all, if you're telling somebody who's an experimentalist or maybe even a particle phenomenologist about the Swampland, then they're going to ask you, well, what's it good for, right? Does it tell you what we should see at our next high energy collider? Does it tell you what dark matter is? Those are the kinds of questions they're going to want to know. You might want to formulate conjectures that answer those things. Or maybe you might want to have conjectures that place major restrictions on low energy model building. Okay, so there's these two competing set of things you might want. Things over here, this is in service of being rigorous and having conjectures that even if we can't prove them, we might really trust them. And over here, this is because we want to do things that are useful for actual real-world physics. And these two things are not necessarily in line with each other, and often they're directly opposed to each other. This is, I think, a point that Hiroshi Aguri likes to make with a plot. I don't remember which axis is which, but it doesn't matter. And if you try to line up your conjectures on a plot like this, they're often kind of going like this. Not completely universally, but as a general rule, the ones that have the most, consequences for, your next cosmology experiment or something are not the ones that are the most rigorously tested in the string landscape. That's because, of course, it's hard to do string constructions that address all of these points also. Sorry? Oh, yeah, you're asking negatives?
No, I mean,
Oh, yeah, so things in this direction? Yeah. That's the hard one, right?
Yeah.
I mean, I think if I was going to handicap things, the weak gravity, even more, I should have started, no global symmetries is way up here. And if you just mean like no exact global symmetries, it's basically useless. If you say something about approximate global symmetries, it moves down a little bit in both axes, right? It It's a little bit less rigorous and a bit more useful. And then kind of closely related to that, the weak gravity conjecture and the distance conjecture. And I think maybe I would, not giving myself enough room, I would definitely place them in this quadrant, not down here, but farther down the no global symmetries. Something down here is like the de Sitter conjecture. Maybe the closest thing I can say is like something like the emergent string conjecture, where it's pretty well supported by a lot of evidence, but it's a little bit more useful than the distance conjecture. It's still not, still not that easy to say, oh, the emergent string conjecture tells us that, this experiment is going to see this, right? It's a hard problem. But both of these things are about asymptotic limits, and the couplings in the standard model are not small. So we don't live in an asymptotic limit, so it's not so easy. Intense. That's, the strong coupling is more than that. Right? This is like a weak coupling. It's not a very small number. We're not living in an asymptotic regime in this. Right? Well, but there's different reasons for that, right? That could just be a totally accidental symmetry. The B minus L violation. Oh yeah, but the real axion is, that was ridiculous to begin with. Of course, if model builders want to go wild, then they're going to hit Swampland constraints, right? But they don't have to do that to agree with experiment. So after making this point, what I'm going to say is that for this talk, I'm going to focus on this corner. And of course, you could take the opposite approach and think about, what are the most phenomenologically applicable conjectures? The danger that you run over here. So over here, of course, you try to rigorously establish things, and the very real danger is that they don't matter that much. Maybe they matter for abstractly understanding quantum gravity, but they don't matter that much for doing phenomenology. The danger over here is, oh, you come up with really powerful conjectures. And yeah, you can even test those conjectures with experiments, but that's not the same as testing quantum gravity, right? Because unless you have a really good reason to think that that's a prediction of quantum gravity, all you're doing is testing your conjecture. That's a different thing. Okay. Now I'm going to stop apologizing for what I'm doing and just going to focus on this end of the plot. I should say that, in terms of this kind of principle of, well, maybe you can motivate Swampland principles by connecting them to other ones, there are some attempts to connect conjectures down here to conjectures up here. So that needs to lend some support. There's still some issues. Like some of these things like de Sitter, well, there's pretty good reasons for this conjecture asymptotically, but again, we don't necessarily live asymptotically in the moduli space, so that doesn't necessarily help us. Okay. Good. So I want to get back to this kind of core ideas in the Swampland, which live over here. Miguel already told you about no global symmetries, so let's move down a notch and talk about the weak gravity conjecture and the distance conjecture. And you can kind of think of those things as, roughly speaking, telling you that it's more like no approximate global symmetry. And there's even some people who have tried to make that more precise, which I'm not going to do now, but I'm just going to give you some heuristic motivation for that. So let me briefly introduce these two conjectures. The idea of the weak gravity conjecture is that it's going to constrain, instead of global symmetries, it's going to constrain gauge symmetries. Maybe more precisely, because if you told this to Nadi Seiberg or someone, they would howl with rage and tell you that a gauge symmetry doesn't exist. It's really about gauge symmetries that are in some sense long range. Well, in the continuous case, which is really the case that's been thoroughly explored, this basically means like an infrared gauge theory. A long-range force with some Coulomb law, or even a non-abelian gauge theory in dimension bigger than 4 also falls in this category. Basically, you don't want something that's confined, so that your asymptotic states can have gauge charge. Yeah. But, you know, of course, on some level, Seiberg is right, that there's no intrinsic notion of a gauge symmetry. For long-range gauge symmetry, you think of it as an emergent phenomenon. There's something there. You have some kind of weakly coupled window, then of course, obviously we have QCD at the electroweak scale. So, but if you go too far, then you're running into trouble. But yeah, I agree. Yeah. I want to avoid saying weakly coupled for the following reason, which is that, at least in the case of U1, there's something that we call the coupling. And that coupling could be 1, and still the weak gravity conjecture tells us very concrete statements, so I don't want to restrict to just weak coupling. Okay. But so for this kind of at least simplest weak gravity conjecture statements, what you want is that your asymptotic states, your macroscopic states can have charge. And so then it's a little bit like a global symmetry, because the charge is going to be conserved, just like a global symmetry. But of course it's gauged, and so that has some consequences, and you want the gauge, the fact that symmetry is gauged, to be obvious enough that it's not like a global symmetry. That's kind of the general idea. So for example, if you had a gauge symmetry with a very small gauge coupling, it might be very subtle that this was gauged for most practical purposes, and that would be very close to a global symmetry. At some point you say, well, now the gauge coupling is strong, it's pretty clear. The criterion that ends up being placed is roughly that the gauge interaction is at least as strong as the gravitational interaction. This is sort of an arbitrary dividing line, but I'll give you some other reasons to think about that dividing line later, and it's the one that's supported by evidence in string theory. So the motto of this, that gravity weakest force because at least for some particle, the gauge force is bigger than the gravitational force. So that's all I'm going to say about the weak gravity conjecture for now. I'm going to go back and be very detailed as much as time allows later, but let me now introduce the distance conjecture. Okay. And there's a reason I didn't want to say weakly coupled here, because as I mentioned, the weak gravity conjecture has something to say about things that aren't necessarily weakly coupled in some sense. But the distance conjecture really is about weak coupling. And I don't just mean like, some Yukawa coupling is 0, I mean like a whole sector has a weak coupling. okay? If I have a whole sector where the coupling is weak, and maybe I'm allowed to tune that coupling to 0, then I have a problem. Because if a whole sector decouples, then there is a global symmetry. Like the energy in that sector will be separately conserved from the energy in the rest of the theory. So I have to watch out for this. So it must be, if quantum gravity doesn't have global symmetries, that it's not going to allow me to do this. So let me go back and say some kinematic type statements. I'm going to think of the no global symmetries as kind of like a kinematic level statement, and these things are like dynamical level statements. Let me make some analogous statements to no global symmetries to set up the distance conjecture, as in how does quantum gravity prevent me from taking this zero coupling limit, the strict zero coupling limit. Probably you've all heard that quantum gravity has no free parameters. Which we mean that everything that we can adjust is dynamical. So if there's a gauge coupling that we can change, it's related to the bev of a modulus. If there's a flux quantum that we can change, there's a brane that allows us to change that flux quantum. Brane. This is closely related to the cobordism conjecture. Right? I'm saying quantum gravity because I don't know any quantum gravities that aren't coming from string theory. And I do think this is true in all quantum gravities. Sorry? Yes. I think the cobordism conjecture essentially says that. If there was some other set of quantum gravities that weren't connected to string theory at all, in some kind of generalized sense, there's a global symmetry there. A deform global symmetry. Did I say the right number? That's different because the superselection happens because of asymptotics. So you do have superselection in quantum gravity in dimension bigger than 2. So they are connected dynamically. It's just that you're frozen into the vacuum far away. So like in ADS CFT, you choose a given CFT, you're fixing your boundary conditions at infinity. You can still connect different CFTs with some kind of interface, etc. It's a superselection sector, not a free parameter. I can change it in the bulk with a brane, with a D3 brane. Good. Other questions? Okay. Good. So all the, at least as far as we know, parameters in quantum gravity are always dynamical. You don't like saying quantum gravity, you may put in string theory, but as far as I know, these are the same things. Maybe that's another Swampland conjecture, and very closely related to this same thing I just wrote here. So in the context of talking about tuning something to 0, that's a continuously adjustable parameter maybe, then I need a modulus. So something about the distance conjecture is that at least in the simplest formulation, I need a moduli space to write down the distance conjecture. one difference with the weak gravity conjecture. Okay. So my moduli space, the dynamics are described by target space nonlinear sigma model. This is my EFT action for my moduli. There's no potential, and this is the kinetic term, and naturally a metric appears here. And this is the metric on moduli space. So in the context of Swampland, the metric on moduli space is always this one, naturally defined in my EFT. Okay, and I should say, for those who try to think about this, in order to define the metric on moduli space, I better go to Einstein frame, because if you go to a different frame, you're going to change what shows up manifestly as a kinetic term for the scalar versus what shows up in the Einstein-Hilbert term. This is an Einstein frame. Okay, good. So when I think about adjusting a coupling continuously, I have a modulus. There's this metric on moduli space. Okay. Now let's come back to this zero coupling question. The zero coupling is not allowed. So the natural conclusion is that if I have some parametric weak coupling limit, what can keep me from taking the coupling all the way to zero is if this lies at infinite distance. And moduli space, which I'll write with a curly M. Okay. That's, in a sense, the only way that this kind of simple theory could prevent you from taking a coupling to zero is if the coupling being zero only happens at infinite distance in the moduli. And conversely, it's thought that anytime I have an infinite distance point in my moduli space, there's always some coupling that's turning off. Maybe the motivation for that is a little bit more vague. It's not quite as obvious that this is to do with no global symmetries, but you can think about the weak coupling as kind of explaining why it's hard to get to that theory. Otherwise, you might think, well, it should be easy to dynamically go from this theory to that theory. The only reason it's hard is because of the coupling. Okay, well, in examples, we always see this to be true. So in this converse statement. But again, these are heuristic motivations, so they're not all rigorous for sure. There could still be, counterexamples to even this statement somewhere in the landscape. We haven't looked at the whole string landscape. Okay. So these are kind of, again, kinematic statements. They're like no global symmetries. Because, all I need to, if the violation would occur if this was, even very far away at finite distance, but as long as it's infinite distance, everything's fine, according to these statements. But there's still a problem because if the coupling is decreasing and decreasing as I go farther and farther out in the moduli space, I can just move out there. I find a theory with a very small coupling, and it looks like it has an approximate global symmetry. That shouldn't be. So there's got to be some kind of other consequence. Something else that tells me that I don't just have to change my modulus to get to small coupling. Something else has to happen. Okay, well, it's not totally obvious at first sight, what should happen. You could go and look at string theory examples and maybe you can figure it out that way. I'm just going to state what does happen and then we'll try to see why it helps. What happens is that there's an infinite tower of light particles. So maybe it doesn't even matter if it's infinite. It goes, a tower of particles that goes at least up to the length scale or the species scale, if you know what that is. But as you go farther towards weak coupling, this tower is getting lighter and lighter. So there's some very definite consequence for making the coupling small, so you get this light tower. Okay, well, why does that help with global symmetries? The reason that this helps is you can explain the weak coupling. Say, for example, maybe my weak coupling is a weak gauge coupling. You can explain why the weak coupling is there as a screening effect. You have your whole tower of particles, sum over loops of these particles in the tower, and there's a screening effect which is going to make your gauge coupling smaller in the infrared. Okay, so in other words, if you go up at high energy scales and you unscreen, you look at the bare coupling, you're going to see a big coupling. So it wasn't really a small coupling to begin with, that's just a low energy artifact. Really intrinsically, it's a big coupling, and so there's not an approximate global symmetry. Exactly. So this is the weak emergence proposal. Which I'm messing up the chronology of these things intentionally. This came much after the distance conjecture. But the weak emergence proposal is basically saying that at high energies, specifically at something called the species scale, all the couplings should be order 1. So there's no small couplings, there's no approximate global symmetry. Yeah, that's right. In a perturbative string limit, it would be the string scale. And like M theory on a big geometry would be the 11-dimensional Planck scale. So yeah, actually, in fact, the string scale, the Planck scale example, this is just, it works fine. For the string scale example, it's a little bit more confusing because strictly at the string scale, the couplings are not big. But at the string scale, you get an exponential density of states and things change very quickly. You can't just do your usual QFT analysis above the string scale, and so you have to think more carefully. What I would say is this is a kind of unification, like all the couplings are big. In the string case, well, they're not big at the string scale, but they are definitely unified. Probably you're not going to have an issue where like one part of the theory is decoupled. No, the string coupling makes everything small. The string coupling is small, all the couplings are small. Every single diagram is weighted by the string. Well, string theory doesn't have global symmetry, so we shouldn't worry too much about that case. But yeah, this emergence proposal, I would say, is kind of a fuzzy idea. There's this strong emergence proposal which tries to make a very sharp statement, but then it becomes a little bit tricky. I'm not going to get into that. Okay. Anyway, I'm just saying this because I want to motivate the distance conjecture. Like I said, the distance conjecture really came first. I definitely don't have to say this first, but it's a nice way to think about it. And to see that the distance conjecture really is somehow related to absence of global symmetries, or absence of approximate global symmetries. So let me write down the distance conjecture. I've given you the very general idea, but now I'm going to be specific. Let me sketch moduli space. Turns out that moduli spaces are often kind of long and thin in the asymptotic limits, which is why I'm drawing it that way, but not important for the statement of the conjecture. So let me pick a fixed point in the moduli space. You might say, oh, this point should be in the middle, but I don't want to have to try to define the middle. It doesn't really matter as long as I don't move this point wherever I put it. And then I'll consider some other point that's very far away from this point. And again, no matter where this point was, as long as I'm going parametrically far away, eventually I'm going to be forced to go out one of these tubes. So this is a statement about being far out in the moduli space. This is the geodesic distance between these 2 points with respect to this metric on moduli space, which is the length of the shortest path. Shortest path is necessarily a geodesic. Okay. And now the statement is really, this is just for reference point purposes, the statement is really about what's happening here. At this point P, as I increase this distance. The statement of the distance conjecture is that there's an infinite tower of particles, or at least going all the way up to your cutoff, where the mass of the tower, the mass of the particles in the tower, is exponentially decreasing with this distance as I go far out in the moduli space. Put an M Planck here, but I'm not really concerning myself with the coefficient here. The point is the rate. So this is the moduli space distance, again, the length of the shortest path. And alpha is some fixed number, which is going to be order 1 in Planck units. Here I mean d-dimensional Planck units if I'm in a d-dimensional quantum gravity. So I set my d-dimensional gravitational coupling to 1. So in these Planck units, this number should be some order 1. Okay. And the fact that you're getting this tower, which is coming down exponentially, can also be motivated by this emergence proposal. So that's one of the nice successes. Again, this idea actually came after the distance conjecture. You can use it to sort of rederive, quote unquote, this exponential dependence. Okay. So now we have been a little bit rough about the weak gravity conjecture. I'm going to give you much more detail in a minute. Sorry, go ahead. So this could be a string scale, depending on the limit you're taking. It could also be a Kaluza-Klein scale. Those are the examples that we typically see in the landscape. The distance conjecture doesn't specify the scale, but in the examples we know in the landscape is always either one of those two things, a string scale or a Kaluza-Klein scale. That's right. So as I go farther and farther out, it goes farther and farther below M Planck with this exponential dependence on the distance. I guess it depends on what you mean by generic, but yeah, if we're far out in the moduli space, then we should see this. It's a slightly complicated question. I think there's this statement that the renormalized, the regulated volume of moduli space is finite. That's like maybe the even earlier Swampland conjecture. I'm not sure how much this has been tested. Mm-hmm. Yeah. You have to watch out, like 2A is definitely not finite, yeah. Yeah, but often you have axion directions, and the axion directions are shrinking at infinity, and that's cutting off the volume. That's kind of why I drew this picture with the shrinking tube. Any other questions? Good. So again, these two conjectures, I'm going to be a little bit more specific about the weak gravity conjecture, although I can motivate not having been so specific so far, because the original paper actually gave really two different conjectures, as I'll explain a little later. But these two different statements are kind of sort of next steps in the Swampland program from no global symmetries. They're sort of like dynamical analogs of the kind of kinematic statement of no global symmetries. And it turns out that there are various strengthenings of these conjectures, which people have come up with. Partly in the course of testing these conjectures, sometimes it's more natural to test a stronger conjecture. And so there's some stronger versions that still seem to be true in the landscape. All right. So now let me focus in on the weak gravity conjecture, probably for whatever time I have remaining. Sure. So I'm going to be strict and say it's true for U1s in 4 dimensions, and for both U1s and non-abelian gauge groups in higher dimensions. In 4 dimensions, non-abelian gauge groups are complicated because the gluons like to make things strong in the infrared. You could have some enough massless charged matter so that it's still infrared free, but then that has other effects on the gauge coupling, so it gets a little bit complicated. For U1s, it does not, because the charged particles naturally decouple if they're not massless. Can happen, that's a special case, but if they're not massless, they naturally decouple in the infrared. And so even if the coupling itself is big, it still has a weakly coupled low energy limit. And the same thing can be said for non-abelian gauge theory in higher dimensions, or even abelian, of course, because then the gauge couplings are relevant. Is that another question? 3D is not so good. U1 confines in 3D, right? There's some attempt by Miguel and company, for example, to talk about the weak gravity conjecture in EDS3. Even that's a little bit dicey. Also, black holes are very different in 3D. Black holes haven't come into the story yet, but they will in a minute. So for the weak gravity conjecture, you're better off in 4 higher dimensions. For the distance conjecture, 3 dimensions is okay. Of course, in 2 dimensions, everything is very different. Okay. Good. So I want to focus on the weak gravity conjecture for a bit. And here we go. I kind of gave this kind of vague reason before, but maybe be a little bit more specific now. I think Miguel told you about the problem of black hole remnants. You have a global symmetry. You have a global symmetry that's exactly conserved, then you have this problem where, as the black hole decays, it's not going to discharge. And then you can, if it's a continuous global symmetry, you can end up with black holes of some finite mass and arbitrarily large global charge. You get an infinite density of states, infinite entropy, everything is bad. Okay, so this is kind of a reason to think about black holes with the weak gravity conjecture. It's not going to lead to the same exact problems, but you might think that the same kind of issue you had here, where you have these stable remnants, you might also not want black holes to be stable in the case where you have a gauge symmetry. So let's think about what happens differently. So let's think about a continuous U1 gauge symmetry. D bigger than or equal to 4. You could also talk about the Cartan of a non-abelian gauge symmetry in D bigger than 4. I also think if you have a n equals 4 non-abelian theory in D equals 4, then you could also do this because it's exactly conformal. So it's a lot more like the U1 case. So anyway, I'm going to focus on U1 for simplicity, but you can keep that in mind. So in this case, the black hole, when it has charge, it will generate an electric field. If you put in too much charge, the electric field gets really big, and eventually it just destroys the horizon. You have no black hole anymore. But there's some maximum amount of charge that you can put into the black hole. Let me define that maximum amount of charge as m extremal, which is something that depends on q. What is this? Is just defined as the infimum of the set of black hole masses for all the black holes charge q. You may or may not have a black hole with precisely this mass. That's called an extremal black hole. Sometimes when you try to write down an extremal black hole, the solution becomes singular, but that doesn't affect this definition. This is just the lower bound. Okay. In general, this might be some complicated function, but if we're in Minkowski space, then there's this nice scaling property where if I take the charge to be very big, then m extremal scales with the charge linearly. So as I take q to lambda q, then for a large lambda, I'm going to get this homogeneous scaling in Minkowski space. It's not true for a smaller charge because you could have derivative corrections. Two derivative order, which is the only thing that matters when the charge is really large, then you get this homogeneous scaling. If you had a cosmological constant, that also will kick in at some point and change. If you want black holes to be able to decay, black hole decay conserves charge and it conserves energy. And mass is energy, right? So if your decay maybe could release some energy as kinetic energy, but it can't release negative kinetic energy. And so what that means is that if you want black holes to be able to decay, a necessary condition is that you have to have some end state, some particle, which has a charge to mass ratio which is at least as big as the charge to mass ratio of your black hole. And to be able to forget about these derivative corrections, for example, let me take the large black hole limit. By large, I mean large mass, large charge. And this will be in the same charge direction. Why do I say charge direction? Well, I might have multiple U1s, or I might have a non-abelian gauge symmetry with a higher dimensional R10, etc. So my charge is some vector. So this is maybe I should be careful. In the one U1 case, this is a necessary condition for this decay. In the multiple U1 case, I could put in a multi-particle state. As long as I have a multi-particle state that satisfies this, then that's also a necessary condition. Well, since I'm picking the same direction, it doesn't matter. In general, that would be a problem, but I'm just comparing. I could think about this as like this is proportional to that. I'm talking about the constant proportionality. So pick any norm you want that's the usual scaling linearly. It doesn't affect the answer here. I was thinking about comparing different charge directions. That would be important. Sometimes, not always. So in the case where you have a BPS state, it always, so I was going to say that this defines what it means for something to be super extremal. That's just a definition for the particle. So maybe have caution because that's not quite the same as having mass less than this bound because of the derivative corrections. BPS states are always super extremal, but they're not always extremal. Sometimes they're extremal, sometimes they're not, depending on the direction. In, say, maximal supergravity, they're always extremal. In other pure supergravities, they're always extremal, and the reason is because the only gauge charges you have are the R charges. They're the central charges, the things that show up in the BPS bound. But in a non-pure supergravity, where you have other gauge charges, other vector multiplets, then you don't have this in every direction. In some directions, you have BPS is extremal, in other directions, you don't. Simple example of that is heterotic string theory on a torus. Heterotic string theory on a torus, then string spectrum, yes. As this form, these are non-negative integers. And then the BPS bound you could translate as the number of right moving oscillators is non-zero, non-negative. When it's zero, they're BPS. And the extremality bound is for black holes, this is bigger than the maximum of these two things, just the charge part. That's BPS. And the extremality bound is and then it depends on Q left squared minus Q right squared, whether you have any BPS states at all, whether you have BPS states which are extremal, or BPS states which are strictly super extremal. So for example, in the case where Q left squared equals Q right squared, then you have BPS states, but they're strictly super extremal because of the -1. Other cases where you have BPS states, then they're sorry, did I say that wrong? Yeah. This is the string spectrum. This is the extremality bound. It's a calculation. It's not obvious, but you can look it up. So this is something that I think Sen out sometime in the 90s. But it's the references in the original weak gravity conjecture paper, for example. They reference the Sen paper where this was first worked out. Question? Yeah. That's all right. Mm-hmm. Mm-hmm. Yeah. Maybe we can talk afterwards. I'll say I have a little bit more to say about the general problem of figuring out this extremality bound in a minute. So now let me state it's sometimes called the mild weak gravity conjecture, or just the weak gravity conjecture. The adjective mild is put there because there's many stronger conjectures that still seem to be true that have been formulated. Let me put the caveat that I'm going to be talking about Minkowski space. Weak gravity conjecture with a cosmological constant is still somewhat of an open problem. There's ideas, but it's not very well tested. So define what rational means in a second. So for any rational charge direction, there's a multi-particle state. Charge in that direction. That's super extreme. What do I mean by a multi-particle state? I mean a bunch of particles that are infinitely separated, so they don't interact. The energy or the mass of this state is just the sum of their masses, and the charge is the sum of their charge. You can think of it as like a final state for black hole decay when all the particles have gone asymptotically far away from each other. Okay? We want it to be super extremal because we want the kinematics of the decay to be possible. What do I mean by saying Q is rational? That means that some multiple of this vector is properly quantized. I have more than one charge direction. If I have, say, two different charges, then there's a dense set of directions that are rational, but other directions are not. So of course, if Q was not rational, there could not possibly be a multi-particle state in that direction. That's why we put that here. And again, this is almost the statement that any black hole can decay. Let me write down the caveats for why it's not quite that statement. So this mild WGC is almost a statement that any black hole can decay. There's two kinds of caveats. One is that extremal black holes maybe can't decay. And this would be if the WGC is saturated. So then the kinetic energy released is 0. So there's no actual decay. You might call this marginally stable. Because if you just put any amount of energy into that black hole, then it can decay. So an example, a prominent example of this would be a BPS black hole. Clearly a BPS black hole is stable, but again, if you add any amount of energy to it, then it is possible, however unlikely, for it to decay. It might just sort of radiate the energy away again, but it could also split up. Okay. And actually, Berry and Vafa, a distinct paper from where they proposed the distance conjecture, proposed that actually this only happens for BPS black holes. So one way of stating this Liguri-Vafa variant of the weak gravity conjecture is that the weak gravity conjecture can only be saturated by BPS states. You have to be very careful, and even in that paper, they think they were not quite careful enough. It's not true that a BPS state always saturates the weak gravity conjecture. Like I mentioned before, BPS is not always the same as extremal. But this conjecture says it can only be saturated by BPS states. And that does seem to be true in any example that we know about. And you can kind of understand why, because if you had something that wasn't BPS, that exactly saturated the weak gravity conjecture, any kind of correction would just push you one way or the other. Right? And if it's not BPS, there's nothing protecting you against those corrections. It would have to be a very special circumstance for it to saturate the conjecture if it's not BPS. I don't know that symmetry, but I'm not saying it can't happen. There's nothing we know about. Certainly there aren't examples in the string landscape that I know about where you saturate this and it's not BPS. In fact, it's even interesting, well, we're still working on this, but I think in perturbative string theory, this might even be true at tree level. Like I just made a statement about loop corrections or something, right? But this may even be true at tree level in string perturbative string theory, where you only ever even saturate at tree level when you're BPS. I haven't quite finished checking that. It's true in the bosonic string. Of course, you never BPS in the bosonic string. Never saturated. Well, loop corrections might push you either direction, but if you didn't saturate at tree level, if you satisfied but didn't saturate, then you don't care, as long as the coupling's small enough. Yeah. I'm saying at tree level in string theory, not in supergravity, but yeah, that's right. Yeah, so you can certainly come up with Kaluza-Klein examples where tree level Kaluza-Klein theory saturates. Okay. The other reason why this isn't quite the same as saying that all black holes can decay is kind of subtle, is that some theories, you have a situation, say, where, for example, all the super extremal states might have, for example, even charge. Not that there aren't states of odd charge, they're just sub-extremal. In that case, then the fate of the odd charged black holes is kind of unclear. Of course, if the odd charged black holes were actually extremal, then they just couldn't decay. But they may not be extremal either. In fact, I would suggest they're not. So this is kind of something which hasn't been explored very much. We pointed this out in 2016. Too much with it, other than come up with more examples like Hector's nice example where we're talking about strings instead of particles, but it has this property also. Well, so this is typically by a small amount, like an order 1 amount. So for a black hole, it's a very subleading distinction. But nonetheless, if you had actually extremal black holes of odd charge, then you don't have light particles of odd charge, so they can't decay. But we don't actually know if you do, because again, it's a subleading piece from the perspective of a black hole. Yeah. There's something else that's odd charged. So if you have no light states of odd charge that are extremal, you're going to get stuck somewhere. No, because you know that those states don't exist at charge 1. In these examples, this perturbative string theory tells you the states aren't there, or they're heavier. It doesn't tell you what the black holes are doing, but it tells you the light states are not there. So you're not going to get stuck at charge 1. You're going to get stuck at charge, wherever perturbative string theory breaks down, at least, maybe higher. Well, the thing is that we don't actually know what's happening with odd charged black holes in this theory. This is a small distinction in like how much extra mass. If they have just a little extra mass, like they can't quite satisfy the same extremality bound, everything is fine. So you can't easily calculate that in, just like a two-derivative gravity calculation. It's a correction. Actually, I don't know. I just mean the black hole extremality bound may not be quite what you think it is, right? You think you reliably calculated this in gravity, but this is a small correction from the perspective of a large black hole. So maybe it's not quite what you think it is. Maybe it somehow depends on whether the charge is even or odd. So what you would do is you create a black hole, which is odd charge and it's not extremal, and then you let it decay. Well, you have odd charge particles. They're just a bit heavier, right? Of course, they're there. If they weren't there, you'd have a different charge lattice. You can still create odd charge black holes. They're just not going to be extremal when you create them. But you can let them decay and see what happens. So again, it's a question of like how reliable is your EFT calculation that's telling you how they decay. There could be some small correction to that, which says that they actually stop a little bit short of extremal. Nobody has answered this question. Kind of a thorny issue about it. These examples absolutely 100% exist. What exactly is going on with them, I don't think anyone knows. 5 minutes? Okay. Good. So let's see what I can say. Let me maybe mention some other forms of the weak gravity conjecture, because this is maybe like the very sharpest and most rigorous form of the weak gravity conjecture, but it's not the most interesting one. So there are other stronger conjectures that are supported by lots of evidence in string theory. I'll also mention, without going into it, but I can talk to people if you want to know about it, is this sort of careful statement that I wrote down is equivalent to some convex hull condition, which you can do graphically. It's just the reason for writing down this careful statement is you have to be careful about charge quantization. So when you write down your graphical convex hull condition, it kind of obscures the issues of charge quantization, which is why I wrote it this way. Okay. Good. The other thing I'm going to not talk about for want of time is so when I first mentioned the weak gravity conjecture, I made this sort of vague statement about, gauge forces and gravitational forces. There is a version of the conjecture which really hones in on that. Instead of using black holes, it talks about, well, is the electrostatic repulsion bigger than the gravitational attraction? So why didn't I do that? Well, you can do that, but there's a sort of an issue, which is if you try to formulate this mild weak gravity conjecture in this force land, which is what we call the repulsive force conjecture, you run into an issue, which is that you don't really know what it means to be self-repulsive, which is the analog of super-extremal, for a multi-particle state. For a single particle, it's just, you take an identical copy, does it repel itself or not? For a multi-particle state, there's multiple notions that you could use, and even just looking at the landscape, it's not easy to decide which is the right one. So for the mild weak gravity conjecture, not only is it nice to connect to black holes, but this is really a sharp conjecture. The repulsive force conjecture is kind of muddy. After I tell you about these tower and sublattice weak gravity conjectures, maybe I can preview. They're not going to involve multi-particle states, and so it's straightforward to take these and replace self-repulsive with super-extremal with self-repulsive. And then you get a priori different conjectures, but in real string theory examples, they turn out to be very closely related. It could be different, but in real examples, they're not. Okay. So quickly, when I take gauge coupling to 0, this is a weak coupling limit. And so the distance conjecture ought to apply. There should be a light tower. You might think, oh, this tower has nothing to do with the weak gravity conjecture, it's just some tower. But if you look at, say, the emergence proposal, that doesn't hold up, because you want your gauge coupling to be small because of a screening effect, and so you really need a charged tower. A light charged tower. And if you even go and you dig into the emergence proposal, and again, this is in the ahistorical order, but if you go and look at the emergence proposal, you see that in order for the screening to work, you need your charged tower to be approximately extremal. Doesn't fix the order 1 constants unless you're maybe over careful about it. but it does give you that rough idea. And so it suggests that you should take your weak gravity conjecture, and instead of just requiring, one particle or some set of particles for, for a given direction, you should have a whole tower of particles. And this is supported in string theory examples. Let me write down what the conjecture is quickly. Our weak gravity conjecture which is for every quantized charge, again, I'm making a slightly more careful version of the conjecture than you might find in some sources, because I'll tell you why in a second. So for every quantized charge, there's an integer, okay, which is positive, such that there's super extremal particle, not a multi-particle state, but a single particle charge P times Q. So, okay, you put in, charge 1, 2, 3, 4, 5, 6, 7, no matter how big your charge is, there's going to be something with an even bigger charge that's super extreme. Not only that, but there has to be something which is a multiple of 3, something that's a multiple of 5, something that's a multiple of 7. It has to, you can't leave out, all the multiples of 3. That doesn't follow this conjecture, and I'll tell you why that's important in a minute. So this is supported by string theory. Let me just mention quickly that these particles here do not have to be stable particles. They can be unstable, which is different from the mild weak gravity conjecture. It's not such a big issue in practice. Usually, in examples that we're checking, they're narrow resonances. They're not just going to disappear right away, so we can still talk about them. But you might imagine that there would be a situation where they might become very broad. So why is this conjecture interesting other than being satisfied in string theory examples? Is that it's automatically preserved under Kluser-Klein reduction. Okay. And this kind of careful statement that I made about this, for every quantized charge Q, there's this integer multiple that's super extremal, is really needed for this. If you just said, oh, there's an infinite power of things with bigger charge that are super extremal and you're not careful, then actually you don't get this automatic preservation. And basically the idea is that you look at some charge in your reduced theory, say you reduce on S1, and now you have an extra charge, which is the graviphoton charge, and you want this tower conjecture to be true, well, you can check that a super extremal particle, all the KK modes are also super extremal. That's not, by the way, enough to satisfy the mild conjecture automatically. But it does work here, because if I have the KK modes of my, I have charge KQ, and I'll pick the one with KK charge KN, K times N, and this guy is also super extremal, so I automatically preserve the tower weak gravity conjecture under this Kluser-Klein reduction. If you're talking about like wrapped brains and stuff, that's a bit more complicated. That may not be automatic, but whenever you're just dealing with this graviphoton, even if it's not a torus, this all works. The reason the mild weak gravity conjecture doesn't get preserved is if you look at this convex hull condition that I mentioned. This is the U1 KK. This is the higher dimensional U1. And if this was my higher dimensional particle, which is super extremal, because, excuse me, this is Q over M space. So super extremal means outside the region where there are black holes. And if that's super extremal, it turns out the KK modes lie on this ellipse here. You might think, oh, this is good. I draw lines between these. It's going to enclose this region, which is the mild weak gravity conjecture. when I make the radius small, these points all the KK modes get smushed up here. And so if I do this quite correctly, you'll see that as the radius gets small, eventually it's going to hit there. You're going to violate the mild conjecture. That's if you just had the single super extremal particle before reduction. If you have the tower, then you're fine. It's a question. Let me just say one more thing. Just one more conjecture, which seems to be true always in the string landscape. Part of the reason for thinking about these stronger conjectures is sometimes thinking about a stronger conjecture makes it actually easier to prove. So, sublattice gravity conjecture. Almost like the tower conjecture, you can just reverse the order of the wording, basically. So instead of saying for every quantized charge, there's an integer, say there's an integer such that for every quantized charge, there's a super extremal particle of charge KQ. So it's very similar to the tower conjecture, but this K is a universal feature of the whole charge lattice, not just something that varies based on which site you pick. And this is the same. This implies, and vice versa, that there's a finite index sublattice of the charge lattice where there's super extremal particles everywhere on that sublattice. And the reason why this is interesting is that this is a theorem. Really put an asterisk here because we're in the process of, making sure that we understand all the possible fine points of this theorem, but this is basically a theorem in perturbative string theory. Which I should say for the NS electric for example, if you're dealing with heterotic string theory, all the electric charges under all those heterotic gauge fields, this is a theorem. Yes, that's right. Now we're dealing with a single particle, not a multi-particle state. So these are resonances. We try to bound the lifetime, not in the conjecture, but in all the examples that we know how to check, it's not typically been an issue that they're so broad that you can't find them. Might be that an example that we don't understand yet, maybe that's why. Not necessarily. Not just that their width is set by the gauge coupling. Maybe you can make a starred version of the conjecture where I say that K is never large. Yeah. Yeah. So emergence demands that K, that doesn't demand a sublattice. It demands that you have a reasonable density of these particles. So however you get that, you can't have just very sparse super extremal particles, or at least unless, emergence would be fine if there's like some very close to extremal but sub-extremal particles. It doesn't necessarily know about the very sharp bound. But it definitely can't deal with just, a very sparse set of extremal particles and nothing else. does seem to be that k is never very large. I've only actually personally seen examples with 2 or 3. I think Curry was just telling me that they have an example with 5. There might be bigger examples, but it's not very easy to just go and find in flat space. But all of these things I'm saying right now are in flat space because the weak gravity conjecture itself clearly needs some modification in ADS. You can kind of talk about black holes that are big in Planck units and small in ADS units, and then use those to define the weak gravity conjecture, and that's probably a right statement. It's a little bit fuzzy because you can't just take away the derivative corrections the way you do for the Minkowski version. But up to that sort of fuzziness, that's probably the right statement, but that hasn't been tested a whole lot. There's other things I wanted to say, but I think we're past our cutoff.